Alright, so in this video we're going to go over some practice problems on the material covered this week. And so starting with section 9.1 here, in this first example, we're kind of going to do a review of our function operations. So for question 29, we're given these two functions here. We're going to perform these operations here in A through D, and then we also want to find the domains of the resulting functions. So starting with A here, we're going to do f plus g. So this is just going to be f of x plus g of x. So we're going to have 4x plus 1, that's f of x, and then we're going to add g of x to that. So that'll be 6x plus 3. So from here, we're just going to combine like terms. We have a 4x and a 6x, and then we also have a 1 and a 3. So we're going to end up with 10x, and this is going to give us, this first one here, this f of x is going to be 4x minus 1. So this will end up being 10x plus 2 here. So that's the resulting function that we'll get when we add these two guys together. Now we also want to find its domain. So the domain of this function here is actually just going to be all real numbers, which we can write as this here in interval notation. And that's because we can plug in any value for x here, and we're going to get an actual output value. There's not a value that we're going to plug in for x that will break this function in any way. Alright, so let's look at part B. We're going to do something similar. Now we're going to be subtracting these functions here. So we're going to have f of x, which is 4x minus 1, and we're going to subtract out g of x. And we're putting these parentheses here because we're subtracting out this whole thing, and this binomial here, this subtraction needs to apply to both of these guys. So this is going to be 4x minus 1 minus 6x, and then minus 3. So from this point, we can now combine like terms like we saw in the last example. So we're going to have 4x minus 6x, which will give us minus 2x. And then we have minus 1 minus 3. So that'll give us a minus 4. And we also want to find the domain of this guy. And as you may have already guessed, this is also going to be all real numbers. We can plug in any value for our x here, and we'll get an output value. All right, let's do the same thing for C. In this case, we're doing f times g. So we're going to have 4x minus 1 times 6x plus 3. So from here, we're just going to use our FOIL property. So we're going to multiply this 4x to our 6x and to this 3, and this minus 1 is going to multiply both of these guys here. So we're going to end up with, let's move this down. We're going to have 4x times 6x, which is going to give us 24x squared. Then we're going to have 4x times 3, which will give us 12x, and then minus 1 times 6x gives us a minus 6x. And then lastly, our last term is going to be minus 1 times 3, so this will give us a minus 3. So we can simplify this one more time here, because we can combine these guys here. This will give us a positive 6x, and then we have this minus 3 here. Now again, we want to find the domain of this guy, and again, this is going to be all real numbers. We can plug in anything for our x values here. We're going to get a nice output value. Alright, let's look at the last one here. We're going to do f divided by g in this case. So we have 4x minus 1 divided by 6x plus 3. Now from here, we can't simplify this any further, so this would be our final answer here. But we need to find the domain of this guy. And if you remember, whenever we're dealing with rational functions, we know that the domain is going to consist of all real numbers except those that make this guy undefined. And with our rational expressions like this, we know this is going to be undefined when we divide by 0. So we need to figure out when our denominator, 6x plus 3, is going to be equal to 0. We can do that by setting it equal to 0 like we have here, and then solving for x. So we'll subtract 3 on both sides here. We're going to end up with 6x is equal to negative 3, and then lastly we'll divide by 6 on both sides. So we're going to get x is equal to negative 3 over 6, or negative 1/2. So this means that if x were to be equal to negative 1/2, if we were to plug that into our equation here for this x, we would end up with 0 in our denominator, which would make this undefined. So that means our domain is going to consist of all real numbers except negative 1/2. So we're going to go from negative infinity up to negative 1/2, but not including that guy, and then negative 1/2 up to infinity here. So that would be our domain for that one. All right, so for this next question here, we're given a function and we want to find its difference quotient, which is given by this here. Now for this problem, it's split up into two parts. First, we want to find the numerator of the difference quotient in part A. So let's do that first. So the numerator is going to be f of x plus h minus f of x. So what we're going to do then is plug in x plus h into our function wherever we see an x. So we're going to have 2 times x plus h squared minus 1. And so this whole thing here is f of x plus h. All right. Then we're also going to subtract out f of x, which is 2x squared minus 1. And since we're subtracting this binomial here, we need parentheses on the outside of it. All right, so from here, let's simplify this a little further. We're going to have this 2 on the outside, but then we have x plus h squared. Well, this is the same thing as x plus h times x plus h. We still have this minus 1 here, and then we know that this minus is going to be distributed to both terms in here. So we're going to have a minus 2x squared and a plus 1. All right, so we'll keep simplifying this. When we're multiplying these guys here, these two binomials, we're going to end up with x squared plus 2xh plus h squared. Now we still have these guys here, and actually we have a minus 1 and a positive 1. So these guys will cancel each other out, and then we're just left with this minus 2x squared here. So in the next step, we want to distribute this 2 to everything inside of our parentheses. So we're going to have 2x squared plus a 4xh plus a 2h squared, and then we still have this guy on the outside. Now notice we have a 2x squared and a minus 2x squared, so these guys are going to cancel each other out. And so our final expression is going to be 4xh plus 2h squared. So this is equal to this guy here. All right, so for part B, we're going to find the actual difference quotient, and we're going to do that by plugging in what we got for part A into the numerator of this guy here. So part B, we have our difference quotient here. So in our numerator, we're going to have 4xh plus 2h squared, and this is going to be over h. Now from here, we can simplify this guy. Both of these terms have a factor of h. So if we factor that guy out, we're left with this here, and this is all over h. Now since we have an h in the numerator and the denominator, these guys are going to cancel, and so we're just left with 4x plus 2h, and so this is our difference quotient for this function here. All right, so for this next question here, we're working with composition of functions, and we've seen this in previous sections here. So given two functions f and g here, we first want to find f of g of x. So this notation here means we're looking at a composition of functions, and we can also write this as f of g of x. So we're literally plugging in our function for g of x into our function f of x. So if g of x is equal to 3x, we're going to plug in 3x wherever we see an x in our function f. So f of g of x is going to be 1 over 3x minus 5. All right, and we also want to find the domain for each of these guys. So again, we're looking at a rational expression in this case. So we know that the domain is going to be all real numbers except those that will make this undefined. And that happens when our denominator is equal to 0. So setting our denominator equal to 0, we're going to get that x is going to be equal to 5/3. So this means if we were to plug 5/3 into this x value here, we would get an undefined function. So our domain is going to be all real numbers except this number that makes it undefined. So we'll go from negative infinity up to 5/3, and then 5/3 up to infinity. And just as a reminder, we're using parentheses here because we're not actually including that value of 5/3 into the domain. All right, so let's do the same thing for this one here. We're still doing a composition of functions, but now we're looking at g of f of x. So this means we're going to plug in our function for f of x into this function g of x wherever we see an x. So this whole thing here is going to be plugged into that x there. All right, so doing this, we're going to have 3 times f of x, which is 1 over x minus 5. And simplifying this a little bit, this is just going to be 3 over x minus 5. Now again, we want to find the domain of this guy, and by similar reasoning, we know that this happens when this is going to be equal to 0, and this will happen when x is equal to 5. So our domain in this case is going to be all real numbers except for 5. So in interval notation, it'll look like this here. Alright, so for the last question in this section, we're given this function h of x here, and we want to find 2 other functions, f and g, such that the composition of those 2 functions will result in the original function that we were given. So for this guy here, notice we have a 6x minus 2, and this whole thing is being squared. So we can kind of think of this when we're looking at a composition of functions. We know that this is the same thing as f of g of x. So this g of x here is kind of like our inside function, and this f of x is like our outside function. So looking at this guy here, what we see is something being squared. So our outside function is this square function, and so we can call just this inside function here x for now. So we're going to say our outside function is going to be f of x, and that's going to be x squared. Now, our inside function, our g of x, is what we're going to be plugging into this x here, so that we get 6x minus 2 squared. So from here, it becomes a little simple. We're just going to make g of x be equal to that inside function, this 6x minus 2. And we always want to check our work to make sure that these 2 functions are going to make this statement here true. So if we were to compose these guys here, if we were taking f of g of x, this would be plugging 6x minus 2 directly into our f of x function here, which is exactly what we started with. Now, something to note with these types of problems here is that there are multiple different answers. So we just want to make sure that the 2 functions that we find actually do make this true. Alright, so in section 9.3, we're looking at parabolas and their applications. So for question 15 here, what we want to do is find the vertex of this parabola, determine which direction the parabola is going to open, find the discriminant, and use that to determine the number of x-intercepts that this parabola has. So first we want to find the vertex, and as you can see, I have this listed here. So this is going to help us determine the vertex of the parabola. If we can transform this guy into this form here, we can easily determine what the vertex is. Now, in order to transform this guy, we're going to have to complete the square. And if you remember from section 8.1, we looked at a version of completing the square. So let's write down our function here. And if you remember, when we want to complete the square, we want the coefficient of this squared term here to be 1. So the first thing that we need to do is factor out this negative. Doing so, we're going to end up with this function here. Now from here, to complete the square, what we saw last time was we were going to add a certain quantity to both sides of our equation. In this case here, though, we're not going to add that quantity to both sides. We kind of want to keep this f of x by itself on the left-hand side here. So instead of adding the same quantity to both sides, we're going to add and subtract that quantity to the same side of our equation. So we know that the quantity that we're going to be adding is going to be our minus b over 2 squared. So in this case, our b is going to be negative 5, so we're going to have 5 over 2, and we're going to square that guy. So the quantity that we're going to be adding and subtracting to now the same side of our equation is going to be 25 over 4. So we have this negative out front. I'm just going to put these brackets here to kind of emphasize that. But we have this x squared minus 5x, and then we want to add a certain quantity, which we found to be 25 over 4. So we're going to add 25 over 4 to this. Now in the same step here, we're also going to subtract 25 over 4, because if we're adding and subtracting the same quantity here, we're not actually changing anything with this function. We're just adding this quantity so that it becomes easy to factor this guy, and we end up with something of this form. Alright, so we still have this minus 3 here, and then something to note, what we've seen with completing the square in section 8.1 is that this quantity here on the outside usually would just be on the left-hand side of our equation. But again, we want to keep this f of x by itself. All right, so from here, what's inside of our parentheses here, this becomes easily factorable. We still have this negative on the outside. I'm just going to keep these brackets here for now. But if we want to factor this guy, this is just going to end up being x minus this quantity that we had here. So we're going to have 5 over 2 squared. And this is always the case when we're completing the square. We're easily going to be able to factor a trinomial of this form that we got by completing the square into something that looks like this here. All right, and then we still have on the outside of our parentheses this 25 over 4 and this negative 3 here. So from here, we can simplify this a little bit further. We still have this here, but if we get a common denominator for these two, we can subtract them. So the common denominator would be 4. So multiplying 3 by 4, multiplying the numerator and denominator of this guy by 4, we're going to end up with minus 37 over 4 here. And then lastly, our last step to simplify this is we're going to distribute this negative to both terms in our parentheses here. So we're going to have minus x minus 5 over 2 squared, and then plus 37 over 4. So notice what we did was we completed the square on our original function here to transform it into this here. Now that we have our equation in this form, we can easily see what our vertex is going to be. So our first point for our vertex is going to be this h value here, so that would be 5 over 2. And then our second point is going to be k, which is going to give us 37 over 4. Now we have to be careful with the signs for our vertex, because notice in this form here, we already have that x minus h is in our formula. So if we have this minus sign here, that means h is going to be positive. The only way that h would be negative is if this is actually x plus h, because if this were a negative value here, by plugging it into this form, we would end up with a plus in this case. So just keep that in mind. So we found our vertex for our parabola. The next thing we want to do is figure out which direction the graph opens up. And we can do that by looking at our a value. So looking back at our original function here, our a value was negative 1. This was the coefficient for our square term. So solely because a is negative, this tells us that our parabola is going to open downwards. So we'll say f of x opens downwards. All right. Now the last part of this question here is we want to find the discriminant and use it to determine the number of x-intercepts. So if you remember from the textbook, if the discriminant is positive, the parabola is going to have 2 x-intercepts. If it's 0, there's only going to be 1 x-intercept, and if the discriminant is negative, there's going to be no x-intercepts. So we would need to find the discriminant by using this here. We have that the discriminant is going to be b squared minus 4ac. So we already know a is negative 1, b is going to be positive 5, and c is going to be positive 3. So our discriminant then, we're going to plug in these values. We're going to have 5 squared, which gives us 25. Then we're subtracting out 4 times a times c. So this would give us a positive 37, and since we have a positive value, this means we're going to have 2 x-intercepts. All right, so for this next question here, we're trying to find a maximum value. We're told that there are a pair of numbers whose sum is 40 and whose product is a maximum. So we have 2 equations just based off of this information here. We're going to say that our pair of numbers is going to be x and y. That's what we're going to call them. We don't know what these numbers are. That's what we're trying to find. So we're told that the sum of these guys, so x plus y, is going to give us 40. And their product, so x times y, is going to be a maximum. We don't know what that value is either. We're just going to call that p for product. So with this information here, what we're going to want to do is actually rewrite this equation here in terms of just one variable. So we can use this first given equation here to write y in terms of just x. So what I mean is, if we were to subtract x from both sides of this equation here, we would end up with y is equal to 40 minus x. Now with this here, with this y value, we can plug this directly into this guy here. And we're going to end up with an equation that just involves one variable. So we're going to have that the product is equal to x times y, and y is the same thing as 40 minus x. Now multiplying these guys together, this is going to be, we're going to have minus x squared plus 40x. So notice we are left with an equation that's going to be a parabola. So if we're trying to find two numbers whose product is a maximum, since we're dealing with this parabola here, and we know that this parabola is going to open downwards, its maximum is going to occur at the vertex of this parabola. So what we need to do is figure out what that is. So using this vertex formula here, we're going to want to find this first coordinate. This is going to be minus b over 2a. So going back to our equation here, our opposite of b is going to be negative 40. And we're going to have 2 times a, which is negative 1. So this is going to give us 20. So that means the x coordinate for our vertex is going to be 20. So if we were to plug this directly into our function that we got for our product, we're going to have, so what we're going to do is plug in this value for 20 into this guy here. Doing so, that'll give us the product that we're looking for, the maximum. So we're going to end up with minus 20 squared plus 40 times 20. This is going to give us 400, and this is the product that we're looking for. This tells us that our maximum value is going to occur at the vertex, and the vertex is 20, 400. All right, but if we go back to the question here, we want to find the pair of numbers whose sum is 40 and whose product is a maximum. What we found was one of those numbers, that's 40, and we found the output value, the actual maximum value, the product. What we still need to do is we need to find this value for y. We can do so by plugging in this value for x directly into our equation that we have for y. So if y is equal to 40 minus x, this means y is going to be equal to 40 minus 20, which is 20. So the two numbers that satisfy this and this here is going to be 20 and 20. So x is equal to 20 and y is equal to 20. All right, so for the last two questions in this section, we're going to be graphing parabolas. So we're going to start with question 29 here. So we want to graph this guy. Now the first thing that we're going to want to do when graphing parabolas is figure out where the vertex is. Now we could complete the square like we saw in the first example in this section to find the vertex, or we can use our vertex formula, and that's what we used in the last example. So for this one, we're going to use our vertex formula, which is written right here. So let's figure out what our first coordinate is. So for our function above, our a value is going to be negative 2, our b value is 4, and c is negative 5. So this minus b over 2a then is going to be, we have minus 4 over 2 times negative 2. So this will end up being positive 1. So this will be our first coordinate here for our vertex, and then we want to find our second one. So we're going to plug in this value for 1 into our original function up here. So we're going to have minus 2 times 1 squared plus 4 times 1, and then minus 5, which will give us a minus 3. So this means that our vertex is then going to be 1, negative 3. So we can easily plot that on this graph here. 1, negative 3 is going to be right around there. Now the next thing that we usually want to do is figure out in which direction the parabola opens up. This will give us an idea which numbers to plug into our function. So if you remember from the first example here, we're going to look at the value of our a. So this will be negative 2 here. Now since a is negative, this tells us our parabola is going to open downward. All right, so in this case, we're also not going to have any x-intercept. So I'll write that here. So this kind of gives us an idea of the behavior of our parabola. So if there's no x-intercept, if this is the vertex and it opens downward, that means the rest of my points are going to kind of occur over here. So that gives me an idea that I might want to pick x values maybe around here and around here to plug into our function. So the first thing that I'm going to plug in is -1. If I plug that into our function here for our x value, I'm going to output -11, which is actually off this grid here, but that's fine. The next value I'm going to plug in is going to be, let's plug in 0. We can see that we're going to get -5, so if we plot that, we're going to get this point here. Now, let's pick another point maybe in this region here. Since we know that this is going to open downwards, it's going to kind of have this shape. So let's pick maybe, well, we already know that our vertex is 1, -3, so that's another point that's already on the graph. Let's pick 2. If we were to plug in 2 into this guy, we would also get -5. So that's another point on this guy. So we're just looking at a rough sketch of this parabola here. So it's going to look something like that there. Alright, so in this last example here, we're again going to be graphing a parabola, but notice that this equation here is in a slightly different form from this one that we saw in the last example. Now this equation is actually in the standard form for a horizontal parabola, which is given by this equation here. Now as you can see, the vertex of this guy is again going to be h comma k, but we just have to be a little careful. Notice our k is going to be within our parentheses here, and this h is on the outside. Now that wasn't the case when we were completing the square for our function, so just be careful of that. Now we know that this is going to be a horizontal parabola, but we need to figure out in which direction that it opens. And just like with our vertical parabolas, our a value is going to tell us that. So if a is positive, the parabola is going to open to the right, whereas if it's negative, it's going to open to the left. So going back to our equation here, our a value is right around here, so this is going to be +1. So this means that our graph is going to open to the right. All right, additionally, we can figure out what our vertex is going to be. Going back to this guy here, our h value is going to be on the outside, so this will be +4. And our k value is going to be inside of our square here. Now going back to our formula, we're going to have y minus k. So the only way that we would have a plus or k value here is if our k value is actually going to be negative. So our vertex in this case is going to be 4, -3. So we can plot that here, that would be this point. And since we know that this is going to be a parabola that opens to the right, all of our x values are going to come from this region. However, when we're plugging in values into this equation, it's actually going to be easier if we were to plug in values for y and then figure out what our x value is based off of that. So in this case here, let's plug in, let's say -2 for our y value. Since we know that this guy is going to open to the right and we're in the 4th quadrant here, most likely we're going to get a nice x value if we plugged in -2 for y. So plugging -2 into here, we're actually going to see that x is equal to 5. So we're going to have 5, -2 as a point there. Let's plug in another value. Let's plug in -4. If we plug in -4 into this guy for y, our x value we're going to see is also going to give us 5. So another point on this parabola is going to be right there. All right, let's plug in -1 and see what we get. If we plug in -1 into this guy, we're going to get a +8. So we're going to have 8, -1. And if we were to also plug in a -5, if you can see a pattern, we're also going to get a +8 here. So our next point here is going to be 8, -5. So our parabola is going to look something like this here. Alright, so this brings us to section 10.2, and we're going to start out with graphing these two exponential equations here. So starting with question 21, we have this equation, and something to note here that I've written down here is that whenever we have exponential equations of this form here, we're always going to have that the y-intercept is going to be 0, 1. So this is going to be a point here. We'll write this in the table, and then we'll plot that on our graph here. So this is our y-intercept. And then something else to note here is that whenever our a is in between 0 and 1, so for example, in this case, 1/3, our graph is going to open up in this direction here. And then if a is a number greater than 1, then it's going to open up in this direction. So what we're going to do is plug in different values for x here and then see what g of x is, and then we'll plot those. So let's plug in a -2. Doing that, we're going to end up with 1/3 to the negative 2 power, which is the same thing as 3 to the positive 2 power. So this will be 9. Similarly, if we plug in -1 for x, we're going to get 3 to the positive 1 power, which is just 3. Let's try plugging in a positive number. If we were to plug in 1, we would get 1/3, and if we were to plug in 2, we would get 1/9. So let's plot these points here. -2 comma 9 is going to be right around there, and then we have -1 comma 3. Now we have 1 comma 1/3, so that might be right around here, and then we're going to have 2 comma 1/9, so maybe right around here. And as you can see, the shape of this graph is going to look like this here, and we're never actually going to cross this x-axis here. If we increase our x values here, our numbers are going to get super close to this x-axis here, but we're never actually going to cross it. So this would be the graph of this equation here. All right, let's look at question 25. So we're going to do something similar, but now we have a little more complicated equation here. So we have 2 to this expression. So in this case, our y-intercept is not going to be 0, 1 because it's not of this form that we saw in the last question, but we're going to do the same thing to graph it. We're just going to plug in different x values and see what we get out. So we can plug in some negative values, but doing that, we're going to end up with very small numbers. So for example, if I were to plug in -2 into our equation here, we're going to end up with 2 to the -6 power here. So this would be 1/64. So this is a really small number and not very easy to graph. Let's plug in a bigger number and see what we get out. If we were to plug in 0 into this x value here, we'd end up with 1/4. So that's a little bit easier to graph. Let's see, if we plug in 1 into this x value here, we're going to get 1, and if we were to plug in 2, we would get 4. So let's plot the last 3 points here and see what we get. So if I plug in 0, we're going to get 1/4. So that's going to be maybe around there, and that's going to be our y-intercept. All right, if I plug in 1, we're going to get 1, and if I plug in 2, we're going to get 4. So as you can see, the graph is going to open this way here, and then if we have really small negative numbers here, it looks like we're going to get closer and closer to this x-axis, but we're not actually going to cross it. So the shape of our graph is going to look something like this here. So for these next 2 examples here, we're going to be solving these exponential equations, and we're going to do so using this property here. It says that if we have an exponential equation of this form here, where we have the same base on both sides of our equation, then it must be the case that their exponents are going to be equal to each other. The only way this raised to this x power is going to be equal to this raised to this y power is if the exponents are equal. So we're going to use this property to solve these exponential equations here. So for question 34, what we're going to want to do is try to get the same equation. So we know that 8 can be written as 2 cubed. So we're going to have this on the left-hand side of our equation. And the reason why we picked 2 is because 32 can also be written with a second base here. So 2 to the 5th power. So using our exponent rules, this is going to be the same thing as 2 to the 3x power on the left-hand side, and then we have 2 to the 5th power. So now that we have the same base on both sides of our equation, using this property here, this means that their exponents must be equal. So we have 3x is equal to 5, and then we can easily solve for x by dividing by 3 on both sides, and so we're going to get that x is equal to 5/3. So that's how we would solve that guy. Let's do the same thing for question 46 here. Now this one's a little bit more complicated, but we're going to do, it's the same idea here. We're going to try to get the same base on both sides of our equation. Now, since the numbers here on the left-hand side, this 4/3 is going to be smaller than the guys on the right-hand side, what we're going to do is leave these guys be. So we're going to have 4/3 x on the left-hand side, and then we're going to try to rewrite these guys as exponentials. Now notice 27 can be written as 3 cubed, and then 64 can be written as 4 cubed. So we can rewrite this as 3/4 cubed. Now, we don't have the same base on both sides, so we are not able to use this property just yet, but we can use our negative exponent rules to rewrite the right-hand side. We're going to leave the left-hand side as is, but if we were to write this as a negative exponent instead, we're going to get the reciprocal of this fraction. So we're going to end up with 4/3 to the negative 3 power. Now notice on both sides of our equation we have the same base, so we can use this property here. This means that their exponents must be equal to each other. So we're going to get that x is equal to negative 3. All right, so for this last example in this section, we're working with a word problem. We're told that the value of a copy machine is decreasing, and that's represented by this exponential function here. Now, t is going to be the number of years since the machine was purchased, and then v of t is the value in dollars. So for part A, we want to figure out the original value of the machine. So the original value is going to occur when t is equal to 0, since t represents the number of years since the machine was purchased. So what we're going to do is plug in 0 into this equation here, and then figure out what v is going to be. So since t is equal to 0, we're plugging 0 into this guy. We're going to end up with 2 to the power 0. And we know that anything raised to the power 0 is just going to be 1. So we're just going to have 5,000 times 1, which is going to be $5,000. So the original price of this copy machine is going to be $5,000. Now for part B, we want to figure out the value of the machine 5 years after purchasing it. So in this case, t is going to be equal to 5. So again, we're just going to plug this value into our function. So v of 5 is going to be equal to this here. We have 5,000 times 2 to the power negative 0.75. So just doing 5 times this negative 0.15 here. Now plugging this into our calculator, this is going to be approximately this here. So this means the value after purchasing it is going to be roughly this much. All right, so in this next section here, we're going to be working with log functions. And I have this guy written on the left-hand side here. So this is going to be what's called log form of our equation. Now we can transition between log and exponential form by using the fact that log and exponential functions are inverses of each other. We're also going to be using this fact here that we saw in the last section, that if we have an equation of this form here, where the bases are the same on both sides of our equation, this means our exponents must be equal. So if we were to go from log form to exponential form, what we're essentially doing is taking the same base on both sides of our equation. So this is written as y is equal to log base a of x. So if we have log base a, then what we're going to try to do is just take base a on both sides of our equation. Now we have an exponential equation here where we have a to the power y is equal to a to this power here. Right, so we're kind of just doing the opposite of what we see in this rule here. If these guys are equal to each other, then this means this is true. So we're rewriting it in this form. Now by doing this, since our log and exponentials are inverses of each other, this is actually going to cancel each other out. What we're going to be left with on the left-hand side is a to the power y is just going to be equal to x. Because when these guys cancel out, this guy comes down here. So this is how we would go from our log form to our exponential form. We would say that x is going to be equal to a to the power y. So we're going to use this property here and this guy to answer the following questions. Now for question 10, we want to write this guy in log form. And the first thing to note is that this is in the exact form that we see here. In this case, a is going to be 36, y is going to be 1/2, and then x is going to be equal to 6. So in order to write this in log form, we just want to write it like this here. So since y is 1/2, we know that this is going to look like 1/2 is going to be equal to the rest of our log function. Now, in this case, a is 36, so this is going to be log base a, which is log base 36. And this is going to be log base 36 of whatever our x value is, so 6. Okay? So we can easily transition between log and exponential form by keeping these two forms in mind here. All right, now for question 17, we want to write this log function in exponential form, and that's exactly what we did up here for this general situation. So what we're going to do then is take this base to both sides of our equation to undo this log here. So if I were to take both sides of our equation to base 4, what's going to happen is we're going to have 4 to this power here, and that's going to be equal to 4 cubed on the right-hand side. Now we know that this log and this exponential are going to undo each other, and so this 64 is going to come down, and this is going to be equal to 4 cubed. We know that this is a true statement here. 4 cubed is in fact equal to 64. So this is how we would write this guy in exponential form. All right, let's move on to question 43 here. Now we're actually going to evaluate this equation, and we're going to do so using the properties we just saw in the last two examples. So if I want to evaluate this guy, it'll be easy to write this in exponential form. So what we're going to do is take base 27 to both sides of our equation. We know that these guys are going to undo each other. We're going to be left with 27 to the x power is going to be equal to 3. Now this just becomes an exponential equation that we know how to solve from the last section. We're going to try to get the same base on both sides of our equation. And this will be pretty simple because we know that 27 is the same thing as 3 cubed. So we're going to have 3 cubed to the x power. And on the right-hand side, we're just going to have 3, but just to emphasize, this can still be written as an exponential. This is the same thing as 3 to the first power. So, since we have the same base on both sides, this means their exponents must be equal. In other words, 3x is going to be equal to 1, and then we can solve for x by dividing by 3 on both sides. So we're going to get that x is equal to 1/3. Now let's do something similar for 64 here. We have a little bit more complicated log equation here, but we can do the same thing. We have log base 3 here, so to undo that, we're going to take both sides of our equation to base 3. These guys are going to cancel out, and so we're just left with this 2x plus 7 on the left-hand side, and on the right-hand side, we're going to have 3 to the 4th power. So from here, we can just solve for x. We're going to have 2x plus 7 is going to give us 81. And then we can subtract 7 on both sides. And then divide by 2 on both sides. So this gives us that x is going to be equal to 37. All right, so for question 55 here, we again have this log equation, and we want to solve for our variable x. So the first thing we're going to do is write this as an exponential. So we're going to take base x on both sides of our equation. So we're going to be left with 1/25 on the left-hand side, and then we're going to have x to the negative 2 power on the right-hand side. Now before we go any further, we definitely want to rewrite this with positive exponents. So we're going to have 1/x squared on the right-hand side. Now from here, you might be able to easily see what our x value is going to be. But algebraically, what we're going to do is cross multiply on both sides. Doing that, we're going to end up with x squared is equal to 25. Now we can take the square root of both sides to get x completely alone. So doing that, we're going to get that x is going to be equal to positive or negative 5. However, we have to be careful with these log functions. The domain of these guys is going to be positive numbers, so from 0 up to infinity. So this negative is not going to be included in our domain. So our only solution in this case is x is going to be equal to 5. All right, for question 85 here, this is going to be a special case. Now we're not going to solve this. We don't have an equation here. We're just going to evaluate this. And we're going to do so using this property here. And it says that if we have log base b of b to some power r, then this is going to be evaluated to just whatever that exponent is, this r value. So essentially, this log base b and this b here undoes each other. So we're going to apply this same rule to this guy, but in order to do so, we're first going to write this guy as an exponent. So this is going to be the same thing as log base 6 of 6 to the 1/3 power. All right, now from here, this log base 6 and this 6 are essentially going to undo each other. So our final answer here is just going to be that exponent, this 1/3. All right, so for this last question here, we're going to be graphing this log function. Now this function can be rewritten as this here, since we know that for our function notation, this f of x is the same thing as y. This is just our output value. Now from here, what we're going to want to do is rewrite this as an exponential equation because it's going to be much easier to graph. So we can do that by taking base 4 on both sides, so that these guys are going to cancel each other out. And then we're going to be left with 4 to the power y is equal to x. So, like I said, this is going to be much easier to graph. We can plug in different values for y and see what we get for x. So for the first value, let's plug in a -1 for y. Doing that, we're going to get 1 over 4 for x. So our first point here, plotting this, we're going to have 1 over 4 gives us -1 here. Now let's plug in another point for y. Let's plug in 0. We're going to get 4 to the power 0, which is going to give us 1. So our next point here is going to be 1 comma 0. Right? Let's plug in 1/2 for y. This is going to give us 2, since 4 to the 1/2 power is the same thing as the square root of 4. So our next point here is going to be 2 comma 1/2. So somewhere around there. And let's plug in another point. Let's pick another nice value for y. If we were to plug in 1 for y, then we're just going to get 4 for x. So our last point that we're going to plot here is going to be 4 comma 1. So our graph is going to look something like this here. So it's actually never going to cross this y-axis here.